Today we want to look at some more derivative stuff. Let's remind ourselves of the things that we know so far. We know our basic rule for finding derivatives. If we have x to some power, to find the derivative of a power of x, we multiply by the exponent and then subtract one from the exponent. So the derivative of x to the n is nx to the n minus 1. We saw this work for integer values of x. We saw this work for radicals, so fraction powers of x. And we saw this work for particular kinds of rational functions. So we saw this work for negative values of n as well. So looks like n can be any number. We multiply by the exponent, subtract one from the exponent. We can get a lot of mileage out of this, especially since we also know that the derivative is a linear operator. That is, the derivative of a constant times a function is that constant times the derivative of the function, and the derivative of a sum of functions is the sum of the derivatives of the functions. The derivative operation respects scalar addition and vector, scalar multiplication and vector addition. Question? The derivative is treating derivative as a noun, and differentiation is what we can name the process. So they're kind of interchangeable. They're almost interchangeable. We can describe the process as differentiation. So we use differentiation, the process, to find the derivative, the name of the function. Kind of the same thing. They're not exactly interchangeable words, but they represent the same thing. Yesterday, I was referring to the process of differentiation. Today, I'm referring to the function, the derivative. The process of finding the function that's called the derivative is known as differentiation. So we can get a lot of mileage out of this, knowing that the derivative is a linear transformation. Knowing that we can that the derivative respects scalar multiplication and vector addition, we get a lot of mileage out of it. This is what we were talking about when I said if we can write powers of x, then maybe we should write powers of x. So, for example, let's suppose I wanted to find the derivative of 2x plus 3 squared. So here I don't have just a power of x. I've got a power of this binomial. Right now, we don't know the chain rule. So if you know the chain rule, pretend that you don't know the chain rule for a while. When we look at this problem, we can see it's just 2x to the second power. If I just expand this, then I will be looking at a bunch of terms that are powers of x. So if I just take the 2x plus 3 and expand it, I can take the derivative of 4x squared. Let's see, 6 times 2 is 12, plus 12x plus 9. So right now I have the power of a sum, but if I multiply that out, I can just turn it into a sum. Then we can take the derivatives a term at a time. If we can write things as a sum of powers of x, then maybe we should. Now, clearly, there are going to be limitations on this as far as our sanity goes. Not limitations on this mechanically, but as far as the things that we would prefer to avoid, Like if I increase this to say 2x plus 3 to the third power, that's not so bad. I would just have to take the 4x squared, 12x, and 9 and multiply by another 2x plus 3. If I just throw on another power, it's not that much work to go into the cubic polynomial, to expand this out. So I've got 8x to the third. My squareds are going to be 12x squared plus 24x squared, so 36x squared. My x terms are going to be 36x plus 18x, so 56, negative 2, 54x, and 27. So the derivative of 2x to the third power, since we're pretending that we don't know the chain rule, we can just multiply all this out and then take the derivative of each of the terms. So 24x squared, 72x, and 54. The derivative of 27, that'll be 0. We can multiply things out. Maybe we should multiply things out. The reason that we're able to get away with this is that we have integer powers of a binomial, and that's easy to expand out. But clearly, this is not going to be a great overall strategy. We could, but do we really want to? Like to a greater degree, like an order of magnitude more than we don't really want to multiply out a cubic, right? Multiply out a cubic, you're like, well, I don't really want to, but that's not so bad. But if I'm like, I'll multiply out 2x plus 3 to the 10th, you're going to be like, oh, no. Even if you have like the Pascal's triangle business and expanding binomials is easy. The only way that you're going to do this with an exponent of 10 is if you really want to show off that you know your Pascal's triangle. We can multiply this out, but we're not going to. There's got to be a better way. So technically we could expand this, but no, let's not. Let's not. Let's not. Now we're going to want to find a solution to this where we don't have to expand, because there will be situations where expansion isn't even an option. So for example, if I said, what's the derivative of the square root of 2x plus 3? Now that I don't have an integer exponent, I've got this 1/2 exponent. Now expansion is not even an option. So I can't take 2x plus 3 and raise it to the 1/2 power and then like just multiply it out into a bunch of terms. We have to remember that exponents do not distribute over sums. We have to expand so we can use the distributive property. Here, that's not an option. For those of you who know, we are specifically going to need to know the chain rule for this last one. We don't technically need the chain rule for the 10th power one, but we're going to want the chain rule for the 10th power one. So really in these first two, we just use the distributive property. This third one, we could use a distributive property, but we don't really want to. This last one, we don't have a distributive property to use. So distributive property, but no distributive property available. But we always want to remember that the distributive property is a thing. So for example, let's suppose that f of x is in this example, I have a quotient of functions. In the previous example, we had some power of a binomial. Now I've got a quotient of functions. So here, since there's only one term in the denominator, we're going to use our try to use the linear transformation aspect of finding the derivative. We're going to use the distributive property and rewrite this function as terms. Trade our quotient for terms. So we're going to use the distributive property. To rewrite this function as terms. So 2x squared divided by x is 2x. 3x divided by x is 3. And 4 over x, for derivative purposes, we're going to read this as 4x to the negative 1. Now that I've written the function as terms, I can just take the derivative one term at a time. So f prime will be 2. The derivative of 3 is 0. And then minus 4x to the negative 2. Or 2 minus 4 over x squared. Or 2x squared minus 4 over x squared. So we had this quotient set up, but since the denominator was just one term, we were able to use the distributive property, and everything worked out. So we use the distributive property. Just like in those first 3 examples, we can use the distributive property. On that third one, yeah, we could use a distributive property, but we don't want to. Questions? Oh, yeah. Since this term is 4 over x, if it's an x to the 1 in the denominator, I can write that as x to the negative 1 in the numerator. That was like the one we saw where we had 1 over x to the third, and we wrote that as x to the negative 3. A positive exponent in the denominator can be a negative exponent in the numerator. Any other way around. I could write 2x as 2 over x to the negative 1, but that would be really weird. Questions? How's everybody okay? Everybody looks all mad. Do I look like this? Is it because it's too simple? Is it possible for math class to be too simple? No one would ever worry about it, right? We've talked about that before. It's what I call 2 plus 3. Let's talk about it. Spend an hour on 2 plus 3. So, all right, tomorrow we're going to do 2 plus 4. Everybody's like, oh, okay, math class is just going to be easy. But later on, when I'm like, I'll chain rule combined with quotient rule for all these weird transcendental functions, you're going to be like, oh, whoa, why do I need to study this? Oh, you didn't complain when we did 2 plus 3 and spent a whole hour on it. Especially considering 2 plus 3 equals 5, there's nothing to talk about. It's just by definition of what we mean by 2, what we mean by 3, what we mean by plus, what we mean by 5, and what we mean by equal. There's nothing going on there. It's just stuff. Here we actually have to have like processes, proofs and shit. Yikes. Any questions? Notice that I distributed the everything is over x. There's one term in the denominator, so I can distribute the denominator up to the numerator. Notice that we don't get to do that upside down. That's not how we add fractions. The reason we can't just flip this over is that's not how we add fractions. So for example, if my function g of x was x over 2x plus 3, I don't have a distributive property to do. I can't just say that this is x over 2x and x over 3. The reason we can't do that is because that's not how fractions work. The distributive property is not available here because I'm not dividing everything by x. I'm dividing x by 2x plus 3. The reason we can't use the distributive property is that that's not how the distributive property works. That's not how fractions work. This is an important thing to remember because the way we abbreviate math, it makes everything look very visual. And we learn these visual forms, but we don't read what's going on in the expression. We don't remember what those things mean. So thinking about adding fractions here, if I've got 2/7 and add 3 plus 3/7, the 2 and the 7 and the 3 and the 7 mean different things. In this case, we're adding fractions, And the over 7 part is telling us that these two fractions are of the same kind. And so the way we would add these is to say 2 plus 3 over 7. So what, 5? 2 plus 3 is 5, right? Spent the whole day yesterday talking about 2 plus 3, and I forgot it was 5. But now I think I got it. We're not doing this because of weird arcane math rules, and because this is how it works. This is just what we mean by addition. We only add things that are the same, and when we add them, it doesn't change what they are. I have 2 of these things called 1/7, and then 3 of these things called 1/7. They are the same. That's why I can add them and have 5 of these things called sevenths. Just like 2x plus 3x is 5x. 2x plus 3x is 2 plus 3x, or 5x. We only add things that are the same, and when we add them, it doesn't change what they are. 2x plus 3x is 5x. It seems weird to say it out loud, but when we're new, we take the math in visually and we forget what things mean. You know very well that if you have $2 and I hand you $3, you now have $5. They don't become something else. But in math class, especially when we're first learning algebra, sometimes I'm like, oh, 2x plus 3x, and people are like, oh, 5x squared. It sounds crazy now because you're all experienced calculus students and you know all your algebra, which is not true. But you know enough algebra to get here, right? So when you're new algebra students, you're just taking things visually. It's like, oh, if I add these numbers, if I add the x's, are there 2 of them now? And that's because we're not looking at this as addition, which is the same thing as you having $2 and me handing you $3 so that you have $5. We only add things that are the same, and when we add them, it doesn't change what they are. If it did, that's not a world that we want to live in, right? You have $2, I hand you $3, and all of a sudden you pull out in your hand, you have 5 pencils. It's like, well, what the hell happened? It's like, oh, sometimes when you take dollars and add dollars, you end up with pencils. Fuck, if I give you 3 of the pencils back, will I have $2 again? And then you hand me 3 pencils. I'm sorry, but 5 pencils minus 3 pencils becomes 2 balls of lint. So now you don't even have pencils. So that's why, even though this is calculus class, I like to emphasize things like we only add things that are the same. And when we add them, it doesn't change what they are. In polynomials, like terms is sameness. In fractions, denominator is sameness. So when we have x over 2x plus 3, I can't split the x over the 2x and then have an x over 3, because that's not how we add fractions. So that the distributive property is not available for the 2x plus 3. We will need some other rule for that. So we're going to need some other rule when we're dealing with quotients. Is everybody okay? So if I have this flipped over like 7 over 2 plus 3, so just speaking of not distributing over here, if I have 7 over 2 plus 3, I can't write this as 7 over 2 plus 7 over 3. Fractions deal in addition in fractions is about common denominators, not common numerators. Common numerators isn't a thing. It's about common denominators. Fractions are about common denominators. Common numerators aren't a thing. I mean, they are a thing, but they don't help us in any way. It's difficult because we represent math and the operations with these symbols. Algebra is great technology. It really allowed us to advance mathematically as a species. But then we have to be very careful about the communication, that we don't just treat it like some kind of visual thing. Does that make sense? I think our primary offender is the distributive property when we first encounter the distributive property. So if I have A parentheses B plus C close parentheses, what's this equal to? AB plus AC. Why can I do this? Yeah, the distributive property, but what is the distributive property telling us? It's the distributive property, yes. What is the distributive property telling you? When I write this, what have we said? Stuff does change, right? This is one way we could do things. This is actually one of the ways that we learn to multiply. If I want to multiply 23 by 17, I can just multiply by 10, 23 times 10, and then 23 times 7. I can break it up using the distributive property. What is the distributive property telling you about? The distributive property tells you that multiplication distributes over addition. It's a relationship between multiplication and addition. We've taken this in. I mean, look how we were stumped when I said, what's the distributive property? What is it telling you? And we all know what it means, but we take in the information visually. The problem that we run into is that when you first learn the distributive property, all I do is hand you a bunch of problems that specifically use this rule. And I don't hand you any problems that specifically don't use this rule so that you know the difference. And so you take this in and say, oh, if there's something out in front of the parentheses, then I just apply it to everything inside the parentheses, right? That's visually what the distributive property is. But is that how it works? Is that how parentheses work? No, because we use parentheses for other things, right? It's not just take whatever's outside the parentheses and apply it to everything inside. The important thing that's missing in this explanation or in this summary is that those parentheses are representing multiplication. If we're multiplying by a bunch of stuff in parentheses, then we multiply by each of the terms in the parentheses. We don't just write it next to each other, even though that's how we represent multiplication. The important thing that's missing from here is the stuff we imply. It's A times B plus C is A times B plus A times C. It's critical that we understand this is how multiplication applies to addition. This is how multiplication applies to a sum. It's multiplication that distributes over addition. This is not just generally how we move parentheses. It's not about the parentheses. That's the other important part. It's not about the parentheses. Because if I have the natural log of x plus y, I can't remove these parentheses just by doing the natural log of x plus the natural log of y. Because when I write natural log in front of the parentheses, I'm not saying multiply natural log. That doesn't mean anything. It doesn't mean anything to say natural log times x. Natural log of what? We can't just like say this is natural log of x plus natural log of y. Not multiplication. I can't use that parentheses thing with the distributive property. There's no distribution here. Not multiplication. Any questions? Happens a lot. We do parentheses and stuff. E to the x plus y. That's not e to the x plus e to the y. Because it's not multiplication. It's exponents. Question? Oh, yeah. I made it extra wrong. Thank you. So the trouble is, when we do the distributive property, sometimes this happens like when you're a kid, so you probably don't remember it. So when we teach you about the distributive, I almost said we learn you. When we learn you is about the distributive property, sometimes you get that it's multiplication, but sometimes you're just taking it in visually, and it depends upon who you are and how you take in information. And it's really hard to determine that. Because if I give you the distributive property, half of you is like, okay, multiplication distributes over addition. Maybe you don't say it that way, but you've internalized it that way. Then the other half of you is like, oh, this is what I do when I see parentheses. Then the problem gets reinforced when I give you a quiz, and all you have to do is multiply over a sum. And then everybody gets 100% on the quiz. I'm like, oh, you guys have got it. When in reality, half of you's got it. The other half were going purely on visuals. And then later on in algebra, when I talk about the natural log, and I have natural log of x plus y, you're like, oh, got it. This is how we deal with parentheses. And I'm like, oh, what's wrong with you? And, you know, typical math teachers get mad when students don't know math. And it's like, oh, what the fuck, dude? They literally hired you because they don't know math. Don't get mad when they don't know math. That's like what you're there for. You know what I mean? It's like when old people say, oh, kids can't drive a manual transmission. Well, did you fucking teach them to drive a manual transmission? Why do you blame people for not knowing stuff that you were supposed to teach them, asshole? Fuck. Oh, the kids can't write cursive anymore. It's like, oh, no one can fucking read it anymore either. Just type that shit. You know what I mean? I get mad at old people. Because it's like the most basic old people shit to say, to like just shit on young people. Kids these days. Fucking get a new line. Get a new line. And it's not even just boomers, it's like all old people. You know how long old people have been complaining about young people? Ever since there have been old people that were around young people. And it's because the young people want to do something different and maybe progress society and do things better. And old people are like, oh, nah, I want everything to be the same. Fuck that. People be talking about, it's like, oh, there should be a minimum age to vote, like from higher than 18. It's like, oh, there should be a maximum age to vote. And I think I might even be past it. Right now, it sounds like I'm on your side, right? Because I'm like, oh, fuck old people. But eventually, maybe I wouldn't be. I mean, you need to know, you're not going to get more conservative as you get older. Society is going to progress around you and you're going to stay the same. That's what you need to fight. Don't be the same. Be open to learning stuff. Do you know what I mean? That's like, if I could give you one thing, like 5 years at the end, after this class is over, you're not going to fucking remember how to take derivatives. I can tell because I do this. I'll show up at your place of business. You're like sitting there working and you're like sitting there, bloop. I'm imagining you working as a checker at a grocery store. So that seems like kind of a cool job. But anyway, so you're like, oh, bloop, bloop, and all of a sudden it's a piece of paper. And you're like, oh, what's this? And you look at it, it's like, oh, math 251, derivatives quiz. And you're like, oh, what the fuck? And I'm like up there, I'm like, oh, that you got 2 minutes to do those derivatives. And I hand you a pencil because I don't assume that you have a pencil. You're like, well, I'm a grocer. And you start, and no one ever passes the quiz. They think it's really funny because I told them that. Now, I'm not going to do that at all. But I do hope that later on, you start to recognize that you getting older and your kids are doing weird stuff. You did the same thing. Society is just progressing. People want to progress and try to do better. Don't hold them back from doing better just because it feels uncomfortable and it looks different than what you do. That make sense? This is really important because you can't listen to like career advice from people my age. The fuck could I possibly know about the job market today? The last time I applied for a job was before y'all were born. How could I possibly be giving you advice on what the job market is like? I've been at the same job for 23 years now. I don't know about what the job market is like. What skills do companies in 2020 are companies in 2023 looking for? How could I possibly know? I haven't even looked. So, yes, math is mostly taught. We teach in this kind of visual language, but we've got to remember that there's always a meaning attached to it. All the symbols that we use for stuff, it's an abbreviation. It's a good advancement. I know y'all hate algebra, but it's great technology. If you want to revolutionize the world and you find yourself back in history, start teaching people algebra. It doesn't even matter if you barely remember algebra. Just say, I'm going to use like this. Just first of all, teach people zero. If you show up sometime before zero was around, it's like, I'll do this. All right, 10 symbols. And then when this column is filled up, you put a zero as a placeholder. And that means none of this column, and then move it over one. And you're like, oh, wow, you were going to be so fucking famous. Oh, by the way, but don't do 10. Try to do base 12, because that would make me very happy if we switch to base 12. So much better, base 12. We can't switch now. We're fucked now. We're stuck with this fucking 10 thing. But if you go back in time with knowledge of math now, and you can switch to base 12 when you introduce zero, you just need 2 more symbols, right? 0 through 9, something to represent 10 like an X, and something to represent 11. Call it DEC and L or something like that. I don't care. Base 12. I'll be very happy. All right, a quick update. I am not going to be available to run a meeting tomorrow. So no class tomorrow. I won't see you again until Tuesday. So no class tomorrow. Monday is a holiday. I'll see you all on Tuesday. But for now, that's it for today. That's it for this week. I'll see you all on Tuesday. Everybody have a good weekend, and thanks for playing.